Good day to everyone. Welcome to our course, and today we are going to discuss about radiation physics. Well, understanding the basic concepts in radiation physics is important, especially in the evaluation and interpretation of the adverse health effects of radiation. Let's start with a brief history of scientists who contributed to this field, the radioactivity. So the modern understanding of ionizing radiation got its start in 1895 with the first scientist, this one. This is Wilhelm Röntgen, and in 1895, he discovered X-rays, and in 1901, he received the first Nobel Prize for Physics. And in 1903, we have here the power couple together with Henry Becquerel, and these are Marie Curie and Pierre Curie. And they were awarded to the Nobel Prize in Physics for their contributions in understanding radioactivity, including the properties of uranium, which is a type of radioactive material. Okay? And sadly, Marie Curie died in 1934 of aplastic anemia, and probably he developed from extended exposure to various radioactive materials. So just imagine the dangers of which were only really understood long after most of her exposure had occurred. So in fact, her papers and even her formulas, all of her notebooks are still highly radioactive, and many are considered unsafe to handle. So they stored in a shielded boxes and required a protective gear or equipment if you want to review those papers. And for the third image, the third scientist rather, is we have Enrico Fermi, and together they are engaged in research on nuclear chain reaction and the process by which atoms separate and interact. So at the University of Chicago, and they have a laboratory beneath the University of Chicago. A typical example when we talk about radioactivity or radioactive material is the famous Manhattan Project. So Manhattan Project was the code name for the American-led effort to develop a functional atomic weapon during World War II. This is very controversial at that time because they created and they used an atomic bomb, and they engage some of the world's leading scientific minds as well as the US military. So just imagine that this is a joint project between brilliant scientists and the US military. Okay, so the president at that time of United States is Roosevelt. So he set up an advisory committee on uranium. So this is a team of scientists and military officials tasked with researching uranium's potential role as a weapon. Based on the committee's findings, the US government started funding research by Enrico Fermi, as I have shown in earlier slides, and also with Leo Szilard at Columbia University. They were focused on radioactive isotope separation, and this is also known as uranium enrichment. And also, they are famous on the nuclear chain reactions. And on July 16, 1945, in a remote desert location near Alamogordo, New Mexico, the first atomic bomb was successfully detonated. So this is called as the Trinity test. So as shown in the figure, this is the first test of an atomic weapon. Explosion 2 seconds after detonation. So it created an enormous mushroom cloud, some 40,000 feet high, and ushering in the atomic age. Also, some of the scientists who are also working on this project, so the team of Oppenheimer, they developed two distinct type of bombs. Okay, so a uranium-based design called the Little Boy and a plutonium-based weapon called the Fat Man. So with both designs in the works at Los Alamos, they became an important part of U.S. strategy aimed at bringing an end to World War II. So if you recall, this little boy was dropped on Hiroshima, Japan last August 6, 1945 at 8:15 a.m. While this weapon, the Fat Man, was dropped on Nagasaki, Japan on August 9, 1945 at 11:01 a.m. And it caused large devastation on the Japanese country or Japanese people. Now, to better understand the concept of radiation, we need to recall first the basic concepts of physics about energy and forces. We need to connect these two concepts for us to better understand the radiation. So if you recall, energy is defined as the capacity to do work. Okay, so here we've learned in our basic physics that we have the kinetic energy and the potential energy. And kinetic energy is that this is the energy that deals with motion. So typical example for kinetic energy is we have the radiant, thermal, um, object with motion, the sound, even the sound, and electrical. Okay? And for the potential energy, typical example for this is for nuclear, chemical, and the stored mechanical and gravitational. Okay? So when we say potential energy, it deals with position, internal stresses, even electric charge. Okay? So they have a electric potential energy. Okay? So basically, energy may exist in various forms. Okay? And understanding how energy is transferred is necessary for understanding the radiation dose. Okay? And also, we need to recall that energy is conserved. So, in meaning, it can be neither created or destroyed, but this energy will be transferred from one system to another or from from one form to another rather. Okay? And energy, this energy is somehow transferred by forces. So if you recall, we've talked about the four fundamental forces which are recognized in physics. We have the strong, the electromagnetic, the weak, and the gravitational force or the gravity. So here, the strong force binds the nucleus, and for the electromagnetic force, it binds the atoms. For the weak force, it deals with radioactive decay. And lastly, the gravitational force, which binds the solar system or the planets in our universe. Okay? So these fundamental forces can be accounted for why the nuclei of all atoms stay together, and also explains radioactive decay. So these energy and forces will be related in terms of radiation, epidemiology, and dosimetry. So when we say dosimetry, it refers to the determination of the amount of radiation energy absorbed by or transferred to a substance or biological material. So when we say biological material, it can be either human body, tissues, or organs. Okay? And energy and how it is transferred explains radioactivity and are relevant for understanding where radiation comes from and how it interacts with materials. And when we talk about radiation epidemiology, it helps us to understand the health effects associated with a radiation exposure. Okay, so for our next slides, we are going to talk about the health effects on radiation exposure. So, therefore, as a summary, the principles of radiation energy and forces provide logical links for understanding radiation dosimetry and radiation epidemiology. So this is the electromagnetic spectrum. Okay, so all life is dependent on small doses of electromagnetic radiation. So for example, during photosynthesis and vision, so it uses a sun's radiation. Okay, so sun's radiation is part of, this is the electromagnetic spectrum. So the human eye can only see a small portion of the spectrum, which is visible, which is the visible light. So this, the wavelength for the visible light is of similar size to a bacteria. Okay, and for the microwave, this one, microwave and the radio waves. So it have a longer wavelength and considered to be non-ionizing. So on this part, we have a UV radiation that is considered as non-ionizing, meaning this is not harmful to us. And some part of the UV here belongs to the ionizing. Okay, so the inverse relationship of frequency and wavelength would say that in this spectrum, energy is low compared to the opposite parts of the spectrum. So here, on this part, the energy is low here compared to the, here, the opposite part of the spectrum. So it includes parts of UV, X-rays, and gamma rays. So in terms of wavelength, they have shorter wavelength and they have sufficient energy to ionize an atom. Okay? So when you are ionizing, or if your radiation is ionizing, so this radiation is capable for producing ions when interacting with matter. So say X-rays, the alpha rays, beta, the gamma rays, and even the cosmic rays. Okay, so when we are comparing ionizing and non-ionizing radiation, ionizing radiation has enough energy to remove bound electrons, causing atoms to become charged or ionized. Okay? While the non-ionizing, it does not have enough energy to remove bound electrons. Okay? So these are the examples: the microwaves, the radio waves, the visible light. Okay? So these are all non-ionizing radiation. Talking about radiation, we should also know about the atom and the radioactive decay. Okay, so the atom, as we all know, the atom is composed of negative charge electrons, the positive charge protons, and the neutral charge neutrons. Okay, so it have a nucleus surrounded by electrons, right? So the forces that bind nucleons together in an atomic nucleus are much greater than those that bind an electron to an atom through electrostatic attraction. And this is evident by the relative sizes of the atomic nucleus and the atom. Okay? So the energy required to pry a nucleon from the nucleus is therefore much larger than that required to remove or ionize an electron in an atom. In general, all nuclear changes involve large amounts of energy per particle undergoing the reaction. And the mass of an atomic nucleus is always smaller than the sum of the rest masses of components. Okay? So the figure shows a helium nucleus, and here, this is a helium nucleus, and it has slightly less mass than the total mass of 2 protons and 2 neutrons. So this missing mass is called the mass defect. And the energy equivalent of the mass defect is the binding energy of the helium nucleus. Okay? So the mass difference or the mass defect is given by this equation. Okay? So where MP here is the total mass of the protons. Mn is the total mass of the neutrons, and this one is the mass of the nucleus, mnuc. Okay? So, according to Einstein's special theory of relativity, so mass is a measure of the total energy of a system. So, the famous Einstein's equation is equal, this is energy is equal to mc squared. Thus, the total energy of a nucleus is less than the sum of the energies of its constituent nucleons. So the formation of a nucleus from a system of isolated protons and neutrons is therefore an exothermic reaction, meaning that they will release energy. So the energy emitted or radiated in this process is mc squared. It's just the mc squared. Okay? Now, what if this process occurs in reverse? Instead of forming a nucleus, energy is put into the system to break apart the nucleus. Okay, this figure. So, the amount of energy required is called the total binding energy. And the binding energy is equal to the amount of energy released in forming the nucleus and is therefore given by E is equal to mc squared. Okay? And this binding energy explains the source of the energy released during radioactive decay. Okay? So, the transformation of unstable atom towards more stable conditions is called the nuclear transformation or just a radioactive decay. Okay? And this nuclear transformation occurs because of instability in neutron to proton ratio or because just nucleus in excited state from previous transformation. And as we all know, radioactivity is a property of unstable atoms transforming to more stable configuration. So they release energy in the form of photons or charged particles, and that is radiation. Now, let's talk about the half-life. Okay? So previously we talked about radioactive decay and its process. Okay? So when an atom that has become stable in terms of energy by emitting radiation will no longer emit radiation. So the amount of a radionuclide decreases over time and radioactivity weakens. The time required for radioactivity to weaken and reduce to half is called a physical half-life. Okay? So, upon the elapse of a period of time equal to the half-life, the radioactivity will be halved. And when a period of time twice as long as the half-life lapses, the radiation will reduce to a quarter of the original state. So, a graph is shown here. So, with the horizontal axis representing the elapsed time and the vertical, we need to use the here. Okay. So a graph here, we've shown the horizontal axis representing the elapsed time and the vertical axis representing the radiation intensity. Okay, so it demonstrates exponential radioactive decrease in a curve, and this is a half-life, okay, which vary depending on the types of radionuclides. For instance, the half-life is approximately 8 days for iodine-131, while approximately 2 years for cesium-134, and approximately 30 years for cesium-137. Okay? So radioactive materials taken into the body will be excreted after being taken into various organs and tissues. And the time required for the amount of radioactive materials in the body to reduce to half through excretion is called the biological half-life and varies depending on their chemical forms or particle sizes. So from our previous discussion, we've already tackled about these kind of rays. These are the alpha, the beta, the gamma rays, and even the X-rays. And today I am going to reiterate about these types of radiation which are ionizing. Okay, so we need to understand how radiation interacts with matter, which leads to an understanding of its penetrating power and how to protect against it. Okay, so emitted radiation or transfers energy resulting in dose. So we have the four basic types of ionizing radiation. We have the alpha, the beta, gamma, and neutron. So alpha, beta, gamma, gamma will also include the X-rays and the neutron. So when we talk about alpha radiation, it happens when the unstable atom emits two protons and two neutrons. So basically, a helium nucleus. The original atom with fewer protons and neutrons becomes a different element. So compared to other forms of ionizing radiation, alpha particles are large and heavy, and they can travel very far, meaning they can be stopped by a piece of paper, here in this case here, or even our skin, or even just a few inches of air. Okay, so that is for alpha rays or alpha radiation. For beta radiation, it will occur when an atom decays by giving off a high energy, high speed particle that has a negative or positive charge. These beta particles are both smaller and more energetic than alpha particles. And there are two types of beta decay. So when a negatively charged particle is emitted from the nucleus, it is called beta minus decay. And the negative beta particle is also called an electron. But it originates from the nucleus, not the electron cloud surrounding the atom. Okay? So, while when a positively charged particle is emitted from the nucleus, it is called a beta plus decay or positron emission, because the positively charged particles are called positrons and they have the same mass as electrons. Okay? And the beta minus decay happens when an atom has more neutrons than protons. And to gain stability, a neutron becomes a proton and an electron. And the proton stays in the nucleus, while the electron, beta minus particle, is emitted. And because the atom gains a proton and loses a neutron, its an atomic number increases by 1. So we've already discussed this one. Okay? And the mass number stays the same because the number of nucleons stays the same. While for the beta plus decay, this is the positron emission, and it happens when an atom has more protons than neutrons. So to become more stable, a proton becomes a neutron and a positron is emitted. And because the nucleus loses a proton and gains a neutron, its atomic number decreases by 1 and the atom becomes a different element. And the atom still has the same number of nucleons, though the mass number stays the same. Okay? So for the gamma radiation and X-rays, here, these are high energy waves that can travel great distances at the speed of light. So it can both penetrate deeply into matter. Okay? So as thick as lead, so it stops a gamma or X-rays. Okay? X-rays are stopped by dense materials like bone, tumors, or lead. These make them useful for medical diagnosis. Okay? For the gamma rays, it can penetrate further with higher energy. Gamma radiation can be used to precisely target and eliminate tumors. It also has a number of uses in industry, agriculture, pest control, and more. So gamma rays are stopped by several inches of lead. Okay? So of thick lead. While the last radiation, this is the neutron rays or neutron radiation, it is created as a result of fission reaction and happens in nuclear reactors. Okay? So neutrons are extremely high energy. So it needs many feet of dense materials like water or concrete to stop them. So neutron radiation can make other materials radioactive and is used to create the radioisotopes used in medical treatments. So what if we will have a photon interaction. So photons are quanta of electromagnetic energy that exhibit both wave-like and particle-like properties. So a photon can be considered to have a wavelength and frequency. So this is a properties of a wave, and as well as the momentum and energy. And these are the properties of a particle. So despite carrying electromagnetic energy, a photon has no charge and has a much lower chance of interacting with matter than charged particles such as electrons and protons. So here we have 6 ways in which photons may interact with matter. So we have coherent scattering, the photoelectric effect, the incoherent scattering, also known as Compton scattering or Compton effect, the pair production, and the triplet production, and the photo disintegration. Okay, but here in this discussion, we are going to focus only to 3 types of photon interactions with matter. So the likelihood of each interaction depends on the energy of the photon and the atomic number of the observer. Okay, this may cause the photon to attenuate. So when we say attenuate, it will lose some of its energy or it disappeared. Okay, a photon interactions are very important when considering how a photon beam interacts with a patient. Okay, so first we are going to talk about the photoelectric effect. The photoelectric effect occurs when a photon interacts with an orbital electron whose binding energy is close to that of the photon energy. So in this scenario, the photon disappears and all of its energy is given to the orbital electron, which is then ejected from the atom with kinetic energy equivalent to the photon energy minus the binding energy. As the atomic number of a material increases, okay, so if you increase the atomic number of material, the likelihood of the photoelectric effect increases rapidly, or it increases as well. Okay, and the photoelectric effect ceases to become likely at energies over 100 to 200 keV electron volt in water, but remains an important factor for attenuation in lead at energies up to 1 mega electron volt. Okay, for the Compton effect, this is the most important interaction in radiotherapy. So it occurs when a photon has a much greater amount of energy than the binding energy of the electron, effectively considering the electron as free. So in this interaction, the photon interacts with the free electron, giving up some of its energy and undergoes scattering. So the electron receives the energy and is set in motion in a different direction. So incoherent scattering or decompton is not directly related to atomic number, but rather the concentration of electrons in tissue. So as atomic number rises, the density of electron falls slowly. So incoherent scattering becomes slightly less likely in high atomic number materials, high Z materials, okay? And it also decreases with energy, but nowhere near as rapidly as the photoelectric effect. And lastly, we have the pair production. So pair production occurs when a photon passes very close to the nucleus of an atom. If the energy of the photon is high enough, the photon may disappear and create an electron and a positron. The new particles move away with the remaining energy of the photon converted to kinetic energy. And the positron will typically annihilate, okay, once it loses its kinetic energy, giving rise to annihilation quanta, meaning this is the two photons with energy of around 0.511 kilo electron volt. And the pair production does not occur with photon energy under 1.022 mega electron volt. So once this threshold is reached, it becomes more likely as a photon energy increases. So pair production is related to the atomic number of material through Z squared. Lastly, we are going to talk about the radiation health effects. Okay, so the radiation effects depend on how much dose we receive. Okay, this is why dose assessment is important. So this is an illustration of radiation exposure, and everybody is exposed to both naturally occurring and artificial background radiation. So we have this, the radon gas from the ground, the food or drink, the cosmic rays, the artificial sources, which deals with medical. So medical, we are also talking about nuclear power, the weapons, and others. Okay, and the radiation exposure is measured in units called sieverts. And this is a chart when we are going to compare exposures. Okay, so these are for dental x-rays, chest x-rays, mammogram, and the fatal here within weeks is if you are exposed within weeks. Okay, and here, if you recall the Chernobyl accident, so this is the typical level, level 6 in Chernobyl workers who died within a month. Okay, so they are exposed for a very long time. Okay, and that is very harmful. And also, if you can see here, these are parts of our body. And for if our thyroid gland is exposed to radiation, it has high cancer risk as the thyroid absorbs radioactive iodine 131. For the lungs, it has inflammation and scarring. For the red blood cells, the effect is low platelet count, spontaneous bleeding. For the stomach, it will cause nausea, vomiting, and internal bleeding. Even the small and large intestine, so it will cause diarrhea, bleeding, and destruction of lining. And for the bone marrow, it depletes of white blood cells up to 50% within 48 hours, leading to high risk of infection. Okay? So radiation exposure can also increase the chances of developing cancer, tumors, and genetic damage. So actually, if we are going to talk about radiation, we need to really understand its effects. And of course, we have professionals who are dealing with this. So we have to listen to them and understand the adverse effects of radiation. So that's all for today. We are going to end about our overview of radiation physics and hope you've learned something from this video. Thank you for watching and hope to see you soon. Bye!